Alright everyone, and welcome back to the AI Research Roundup. I am Alex, and today we're looking at a fascinating paper from the Papers with Code trending list, published March 16th, 2025. It's titled MTGS, Multi-Traversal Gaussian Splatting. So, this research introduces a new way to create really high-quality 3D reconstructions of driving scenes. It uses what's called multi-traversal data, which is just data gathered from many different trips through the same location, like on a daily commute. The core idea, MTGS, uses an approach called Gaussian splatting to represent scenes with many 3D points, and it cleverly separates the static background from moving objects and changing appearances. And for those of you who want to dig into the nitty-gritty, or perhaps even experiment with this yourselves, the authors have also shared their code. You'll find their MTGS repository on GitHub. It contains the code for this multi-traversal Gaussian splatting work, tools for the new planned dataset, and even released model checkpoints. Looks like a pretty complete package for those interested. So, to give you a visual, in the paper really shows off what MTGS can do. On one side, it displays the same roadblock captured during 3 different traversals under varying lighting conditions from cloudy to sunny. You can see both the car's perspective and a bird's eye view, and MTGS handles these appearance changes really well. Then, on the other side, the figure demonstrates view extrapolation, which is the system's ability to generate new viewpoints. It shows high-quality views even when shifted significantly, like 2 lanes over from the original path. Okay, so showed us the impressive results, now gives us a peek under the hood at how MTGS actually works. It starts with the multi-traversal data and constructs their multi-traversal scene graph. This graph has 3 key parts: a shared static node for background geometry and its fundamental color, represented using spherical harmonics, or SH, which are special functions for things like color. Then, appearance nodes adapt to lighting per trip, and transient nodes model moving cars. The system also uses LiDAR-guided exposure alignment and is trained with several types of supervision, ensuring the rendered images look right, the 3D structure is accurate, and surfaces are smooth. Alright, building on that understanding of the MTGS architecture, now directly compares its performance against another method called OmniRe, specifically looking at how well they generate novel views when trained with an increasing number of traversals. The results are shown using radar charts. So on the left, for OmniRe, we see that adding more traversals, from 1 to 5, doesn't always lead to clear improvements across all metrics. For example, while peak signal-to-noise ratio, or PSNR star, which measures image reconstruction quality, shows some gain, other metrics like LPIPS, a perceptual similarity score where lower is better, don't improve as consistently. But then, looking at MTGS on the right, it's a different story. As more traversals are used, the blue shaded area, representing performance, consistently expands. This indicates better scores across metrics like SSIM, which is structural similarity, ABSREL, or absolute relative error for depth accuracy, and delta 1, another depth accuracy measure. Essentially, MTGS really benefits from seeing the scene more times. Okay, so MTGS clearly benefits quantitatively from more traversals, as we saw in those radar charts. Now gives us a direct visual taste of this superiority. Here, we're comparing rendered images from MTGS with those from OmniRe and the basic 3DGS. MTGS produces images with higher fidelity, handles appearance variations well, and is much more robust when extrapolating to novel views, as seen in the top row. Plus, its transient nodes accurately capture dynamic details like moving shadows in the training examples, which the other methods don't handle as cleanly. So we've seen how multi-traversal Gaussian splatting really pushes the boundaries for rendering dynamic scenes. Its ability to leverage those multiple passes or traversals over the scene data allows it to capture tricky transient effects and generate much more realistic and robust views. This work is a significant step for creating immersive 3D representations from video. Thanks for tuning in to the AI Research Roundup. I'm Alex.